A continuación, contamos con la siguiente ponencia. Esta sería de manera virtual, la cual es titulada Hymenet Continuous Measure of in situ Profiles of Soil Moisture and Salinity Network of Autónomos IoT Sensor. Quien está a cargo a nombre del doctor Xavier Chavanne de la Universidad de París, Francia.
Buenos días, todo el mundo. ¿Me oye bien para la presentación?
Sí, sí se le escucha.
Espera un ratito. Tengo que compartir eso. Mi- Aquí mi presentación. ¿Se puede verla?
Y ya se logra ver la pantalla.
¿Puedo empezar entonces? ¿Me oye?
Se le escucha.
My presentation will be in English. So this is the development of soil sensor, in situ soil sensor for vertical profiles of basic variables of soils. The sensor at the same time is an autonomous object for duplication and to set up networks. This is the work with my colleague Xavier Chavanne. Last development of the sensor occurred within a national research program for observatory, environmental observatory, so no nuclear in this presentation. Name of the research program is Terraforma, and they are funding the last developments of our sensors. So first, okay. Interest in situ water content of soil, but any porous medium. Of course, hydrology, agronomy, but in civil engineering too, there's a lot of interest to have this sort of sensors. But the challenges are very high. There exist already many sensors to measure soil moisture, but they encounter a lot of difficulties. It's why there is always room for a new sensor which can overcome these challenges. This is also user requirements. Why it is so difficult to measure soil humidity? It's because soil is a heterogeneous medium with three phases, solid, air, liquid, which is very different from air. Air humidity is easy to measure. We need continuous monitoring, so it's only possible with digitalization, and it's not possible with direct measurements, so you have to rely on another soil variables, real permittivity. In situ measurements implies electrode in soil, so you have problem of invasiveness, you have problem of representativity. You want to capture intense rain, so very short time. At the same time, so you want to look at the climate change, so over years. So you need a sensor which operates over years. You have also problem of spatial resolution, especially vertical profile. Humidity varies a lot along the vertical profile, but you have also lateral variation, and this can be captured by network of sensors. Networks means you have to duplicate your sensor, so you need to have a very cheap sensor. And there is also a lot of problem in observatories, installation, maintenance, and of course data retrieving. What is our sensors? The name is Hymenet. It stands for hydrological measurement, so it is a measurement part with novel circuits, and there is a network part. And this deals with Internet of Things technology. We adopted recent technology to be able to have a compact sensor, autonomous sensor, like in the photo. And of course, if you want both the measurement quality and the cost, it's very difficult, and so you have to need some optimization. $500 is about some is an order. You can see a box. The size is 12 centimeter, and with three probes in the soil to capture a vertical profile. This year, 2026, is a very important year for us because we want to go from prototypes, from laboratory in some sort, to industrialization, series of 5 to series higher than 20, even 100, to be deployed in observatory all around France and even overseas. And we have, this is the 4th generation of our sensors. It's especially designed for this goal within Terraforma program. And it has 3-4 years of existence, and we have different prototypes to test on fields, and of course to deal with the errors we found. I will deal with the autonomous aspects, and especially autonomous in energy transmission operation. And we use a new recent technology for communication called LoRaWAN. LoRaWAN stands for Long Range Wide Area Network. I don't know if you know this mode of communication, but really it's sort of revolution for the sensors, especially for us. It's very popular in France. It's an open industrial standard since 2015. It means that everybody can set up the network. In practice, you have university with its network, LoRaWAN, and Terraforma has its own network. But a French telecom company like Orange has also its network. We use both for our experiment. It's a long range, 10 kilometers. We experienced that. Low consumption. And well, you pay all these advantages, you pay with a drawback. But the drawback presents no limitation for us. This is the number of bytes in the payload of packet sent. And we have, with this limitation, we can send all the variables we need for our experiments. So we adopted this model of communication very early. Here, with present prototypes in the map of France, we have some sensors spread in some parts of France. And we have some have operated since December 2024, especially this one, which is in Alps, mountain Alps at more than 2,000 meter elevation. And we have also project with the university laboratory to place some sensors in Paris parks. What about energy? Of course, there is a lot of work to reduce the power and the active time of the operation. And we use lithium-ion, a rechargeable battery, in order to use solar cell. It works quite well. You can see this on the operation of the sensors in Lotare Pass over more than 1 year. So here you have a time period. On this graph, you see first the blue lines correspond to points lost during the transfer. It's not very much, in fact. Radio communication may produce this sort of losses, but in normal condition, there is less than 2% messages lost, which is not very important. There is two problems we encountered. First one it's winter, in Alps, there's a lot of snow. The sensors are covered by snow, up to 2 meters of snow. And sometimes it's getting very difficult to communicate, but it's not very much lost, especially there's nothing that happens under the snow. It's very quiet. The main problem is the gateway. The station will receive the message. If out of service, it can be very detrimental. About energy, this is a black line, black curve at the right-hand side vertical axis. And we have the voltage of a battery. Lithium has its voltage varies with the state of charge and goes up to 4, when fully charged, it's 4 volts. So you can see during more than 1 year, voltage doesn't change much. The consumption is not very high. And you can see in summer, the recharge is you recharge very well. It's very sunny in mountain. Now I will talk about measurement quality, which is extremely important for our sensor to be different from previous sensor. Principle is, as I said, wheel permittivity. To obtain wheel permittivity, you have to insert 2 electrodes in soil and apply an alternative electric field between. Problem is not it. Principle is quite simple. Problem is soil is complex. To be sensitive to water molecules, which are dipoles, powerful dipoles, you have to operate at a very high frequency, 10 megahertz. Another problem is there is ion in water, and ion produce another response to an electrical field, and both can be mixed if you don't have the right sensors. Another constraint is on electronic circuit, especially for commercial sensors. You need a digital output, you need to reduce consumption costs, and at the end of the day, sensors you found in shelves, in commerce, are very basic, and they have a lot of biases. For instance, the output mix a bit of 2 responses, 2 soil responses to an electrical field. So this is the principle. What is the technique, really the electronic circuit to exploit this principle? There is 2 big families with a lot of sensors, but we can group them in 2 families. Propagative one, velocity of electromagnetic signal depends on permittivity, and the capacity. The 2 electrodes are a capacitor. And you have also the conductance. What we have done is actually our circuit is the Western bridge, if you know it, but a special Western bridge. The interest is very high phase resolution because we can separate the 2 responses on the electrical field. Our circuit is also a very linear output to what we are interested by. In first stage, we have admittance, the admittance meter, and so we can also model all the circuits. And the second step, you add the electrodes in soil, and there are admittances, and from a geometric coefficient, we can deduce the permittivity and the conductivity. We model with physical relationship all of that in order, because it's not perfect. And the interest of physical modeling is you can relate specification of parts of sensors to all the qualities, parameters of the instrument. For instance, temperature, electronic temperature drift can be estimated with specification. And we have also onboard reference because it is an admittance method. So we have very on board, we have capacitors and conductors to check the quality and any drift. Here is the range in terms of permittivity and electrical conductivity the range permits us to measure water, pure water. Conductivity a bit limited, but for all the salts we have studied, it's not a limitation for the moment. The last step is to convert this electrical variable to what we need, water content and salinity. And this, because of all this work previously, we can say this quantity are soil specific, and there is a great literature to convert independent of the sensor. Here is the formula we used for our conversion. And within the quality, measurement quality, we have to take into account also the design, the geometry design of the sensor, and especially the probes in soil. And here is the geometry, the picture of the geometry. Here the photo with the 3 probes. Each sensor has 3 probes at different lengths, but the probe is made of an inner part to fix the depth, and the sensing part, the electrodes, and where is done the measurement. In this, we can have 3 depths, 3 horizons at different depths, down to 60 centimeters, but we have some choice also. I will finish my presentation by some results. That's time series of variables at different depths. And from this, we can study water balance and filtration, for instance. Here is for one horizon at 15 centimeters. This is still the sensor at Lothar Pass. And they say you have 3 variables here, and one horizon, so horizon at around 15 centimeters. The blue line at the left axis is the salinity, soil salinity after convection. The red is the moisture, water content in soil, and the green is the temperature. Unfortunately, thermometer does not work yet, so we use a temperature from a meteorological station, Courtésie Jardin du Lautaret. As you can see, I think I will need more times, please. You can see that the green line, the temperature, correct very well with the salinity, which is normal. Due to ion transport in water. But what about the water content? There is the diurnal cycle, but it's different from the diurnal cycle of the soil temperature. And here I will finish here, but due to here is the moisture given by the sensors at 3 different depths investigated from the surface to 45 centimeters. We take into account the horizon height to deduce the volume of water of each horizon. And at the same time, from data from the meteorological station at Lothar Pass, we measure what we determine what we call the potential evapotranspiration, according to a formula of the Food and Agriculture Organization. This is well known in agronomy community. And you can see there is very similar behavior between water content measured by our sensor and evapotranspiration, what means water which is evaporated by vegetation at the surface through its roots. Here I have made the sum of the water content of the 3 horizons to have water content of over 45 centimeters, and we can see a very close relationship, very close behavior between the two, whereas the red curve is done by our sensors, the dark one is from data from meteo station of Jardin de l'Hôtel. So this is thanks to our resolution, our low temperature drift with electronic receive, not other sensors are not able to perform. And it's nearly finished. Just to show you, in the case of these sensors, moisture variables, I have forgotten to tell you, this is over 5 days last year, was very dry period. But not as dry as now we experience. And here it's the salinity, and over the same period, and they have very different behavior between both. While at the start, it was the same alternating signal, and our sensor were able to separate what is on phase and what is on predator of phase. Yeah, my end of my presentation. Thank you for your attention.
Muchísimas gracias al doctor Xavier Chavanne. Tenemos una pregunta para el doctor de parte del público y la cual... Sí, sí me escuchan, Javier.
Sí, escucho.
Ok, perfecto. Ok, la pregunta dice, given the system uses low run one network to report the real-time readings every few minutes, achieving a data loss rate of less than 2%, what were the main network over challenges when deploying the system in geographical complex environments such as the mountainous Alpine region or a green roof in Paris?
I'm not sure to have well understood. So it is about LoRaWAN, is it? Please, can you repeat the question? ¿Puede usted repetir la pregunta?
En el chat, ¿podría usted también verificar? No sé si logra ver la pregunta.
El chat. Oh, disculpe, no había entendido. Yes, English. Yes, main problem is gateways. That's the crucial point of LoRaWAN. And so, in case of low-tariff pass, there is 2 gateways, and there is a large area when one gateway can cover all the experiments going on this path. So, the advantage of LoRaWAN is the long range. It's its name itself, long range. So we have seen already in other experiments, we can send messages over more than 10 kilometers. And even there is experiments with satellites and for 100 kilometers, but you have more losses. But that's true, that's the main point of LoRaWAN. I mean, you must be careful on gateways. Must be this problem of line of sight of sufficiently high to cover all the area of interest. But in Brittany, for instance, where we have sensors, there is only one gateway, which is also 5-6 kilometers away, but it's in height, and there's not much loss. It's about few percent too. So it works quite well.
Muchas gracias, don Javier, por contestarle la pregunta. A continuación tenemos una pregunta por parte del público. Le invitamos a ponerse de pie para que la cámara lo pueda enfocar.
Thank you very much, Xavier. I'm glad to see you again. I don't know if I can ask in Spanish or French, but so, en español está bien. ¿No? Realmente gusto en verlo también, le agradezco que nos acompañe hoy aquí. Realmente quiero comentar que las mejoras que ha tenido el instrumento, la sonda, son bastante impresionantes, ¿verdad? Y primero extenderle una invitación que nos pueda visitar algún día por acá y tenés, pues, lo podemos recibir en brazos abiertos. Una preguntita es con respecto a la frecuencia. No sé si todavía manejan la parte de frecuencia fija o hacen un barrido de frecuencias o análisis frecuencial del instrumento. Y muchas gracias por su presentación, Xavier. Y saludos, y me saluda también a Franji.
Gracias, Ian. La frecuencia de la medición, quieres decir. Voy a ver en mi presentación, porque hay también la frecuencia de la transmisión, pero supongo que se trata de la frecuencia de la medición aquí.
Exacto, la frecuencia, esa, exactamente.
Eso es, del campo eléctrico. Es verdad que es importante porque hay en el suelo, la complejidad del suelo hace que hay distintos dipoles. Lo que buscamos son la respuesta de los dipoles al campo eléctrico. Y esos son experimentos y hay que hacer más porque sobre los artículos que he encontrado con mediciones rigurosas, me parece que hay que trabajar a más de 10 MHz. Por el momento, el circuito utiliza quartz a 24 MHz. Es posible, ahora que tenemos toda la física del circuito, es posible trabajar un poco más que 24, si es necesario, porque el problema es que más alta la frecuencia, más importantes son los parásitos, los impedencias parasitas que impiden medir la admitancia de los electrodos. Es el problema. Pero ya con nuestras mediciones no hemos encontrado problemas a trabajar a 24 MHz. Quería aprovechar para deciros, porque he un poco olvidado, es que eso nuestro, entonces compartamos un programa científico para fabricar en serie de más de 20 nuestros sensores. Sensores es muy distinto de lo que has visto, Jan. Hay mucho progreso por encontrar, por satisfacer esta meta de más de 20. Debe ser fabricado bastante fácilmente. Pero eso es dentro del programa Terraforma. Pero ya lo hacemos ya, es que se puede Vosotros, por ejemplo, si algunos son interesados y tienen el dinero, podemos colaborar para fabricar. Es lo que ha ocurrido con el laboratorio aquí, afuera de Terraforma. Entonces, hay toda la documentación para fabricar su propio Hymenet. Hay la parte electrónica y la parte mecánica. Y con mi ayuda también. Sí. Yo he terminado. ¿Hay otra pregunta?
Si una de las personas, parte del público, tiene una pregunta, puede levantar la mano, ponerse de pie para pasarle el micrófono. Parece que ya no tenemos más preguntas, don Javier. Más bien, muchísimas gracias a usted por atenderlo esta exposición.